Okay, in this video you're going to learn how to graph reciprocal linear and quadratic functions. So here's an example of a reciprocal linear function. Notice the function in the denominator is a linear function, a degree 1 function. And this function here is a reciprocal quadratic function because the function in the denominator is degree 2. So you're going to learn how to graph both of these and some general properties of both of them, and learn what the possibility for all of the shapes of what these graphs could look like are. So when you're ready to get started, head on over to jensenmath.ca. Now we are in the advanced functions course, and this is the last unit where we're working with rational functions, and this is lesson 3, the reciprocal of linear and quadratic functions. You can get a blank copy of the lesson here, and you can try the practice problems after by clicking on Student Worksheet. And after you try out the practice problems, click on Worksheet Solutions, so you can check your work and make sure you've done the graphs all properly. So let's get started. Now the first part of this lesson is an investigation where I give you the graph of a linear function, and in blue you'll see there the graph of its reciprocal, and I ask you some questions about both of those functions. And then part 2, same thing, but I give you a quadratic in red, and in blue is the graph of its reciprocal, and then I ask you some questions about the graph. I want you to try those parts on your own, and where I'm going to start by actually showing you example 3, part A, B, C, and D, where we actually go ahead and graph reciprocal linear and quadratic functions. And as we do the graphs, I'll talk to you about these properties that you should have figured out by doing those 2 investigations. So let's do these graphs. So 3a is a reciprocal linear function. When we're doing the graph of a reciprocal function, it's often very useful to come up with the properties of the function that is in the denominator and use those properties to help us figure out what the graph of its reciprocal looks like. So I'm going to divide my work into 2 parts. One part, I'm going to look at the function 2x minus 1. And the second part, I'm going to actually look at its reciprocal, so 1 over that function. 2x minus 1 is a function you should be very familiar with. It's a linear function, slope of 2, y-intercept of -1. Let's write down some key properties of it. When you're doing a reciprocal linear function, the one key property you want to make sure you know is the x-intercept. So the x-intercept would be the x value that lets y be 0. So if we set y to 0 and solve, we would get x equals a half. So there's an x-intercept at the point a half, 0. Now I'm going to make a table of values for this function, making sure I put the x-intercept in the middle of that table of values. So I'm going to put 0.5 in the middle, and then just choose a couple points on either side of it. I'm actually going to choose 3 points on either side of that. So to the left of 0.5, so x value is less than 0.5, let me just choose 0, -1, and -2. And then to the right of 0.5, so x value is bigger than 0.5, I'll choose 1, 2, and 3. It's important I'm choosing points on either side of that x-intercept because that'll make sure when I graph its reciprocal, I get points on both branches of the hyperbola. So now let's calculate the y values that go with each of these x values by plugging them into this function, y equals 2x minus 1. If I plug in -2, I would get a y value of -5. Plug in -1, I get a y value of -3. Plug in 0, I get -1. Plug in 0.5, I get 0, the x-intercept. We already knew that. Plug in 1, we get 1. Plug in 2, I get 3. Plug in 3, I get 5. So these points would show me what the graph of the function in the denominator looks like. It shows me what that linear function looks like. Let me just plot those points because the question actually does ask us to graph the function in the denominator as well. So we do need to graph that 2x minus 1 function. So there's what that function looks like. There is the y equals 2x minus 1 function. We're going to use the properties of this function to figure out what the graph of its reciprocal looks like, because that's actually what we're really interested in. One of the main things we need to know about the reciprocal function are where its asymptotes are going to be. Reciprocal linear functions actually always have a horizontal asymptote at y equals 0, unless it was shifted up or down by some value added after. But if it's just a reciprocal linear like this, the horizontal asymptote is at y equals 0. And in fact, anytime the function in the denominator is a higher degree than the function in the numerator, we have a horizontal asymptote at y equals 0. Because as we plug in bigger and bigger values for x, the denominator becomes increasingly bigger than the numerator, making 1 over a bigger number become closer to 0. That explains our horizontal asymptote, but it also has a vertical asymptote. So keep in mind this function is the reciprocal of this function. So whatever the y values for this function were, for the exact same x values, these y values will be 1 over those values. So whenever this function is 0, this function will be 1 over 0, which is undefined, which would mean a vertical asymptote. So what I need to do is figure, okay, well, when was this function equal to 0? We figured that out right here when x was a half. So if x was a half, the denominator would be 0, which would make the whole function be 1 over 0, which is undefined. So there's a vertical asymptote at x equals a half. With a reciprocal linear function, make sure when you make the table of values for it, make sure for x, make sure you put the vertical asymptote in the middle. And as long as we use these same x values, which we should do since we made that table, notice that that vertical asymptote is in the middle. That's why I put it in the middle over here. So we're going to use the exact same x values. My vertical asymptote is in the middle, and I have points on either side of the vertical asymptote, which ensures I get both branches of the hyperbola it's going to form. So when you're making these tables for the linear function, make sure you put the x-intercept in the middle, which then ensures the vertical asymptote goes in the middle when you do the table for the reciprocal function. Now to get the y values, like I said, this function is just 1 over that function. So to get the y values, I just use these y values and do 1 over them. I just do all of their reciprocals. So I'm just going to do 1 over each of the y values from here. So to get the y value that goes with an x value of -2, well, when I plug -2 into this function, I get -5, which means when I plug it into this function, I get 1 over -5, which is equal to -0.2. And then just follow the same trend. Just take the rest of these y values, put all of their reciprocals over here. So 1 over -3 is -0.33 about. 1 over -1 is -1. 1 over 0 is undefined. That's why there's a vertical asymptote there. 1 over 1 is 1. 1 over 3 is 0.33. And 1 over 5 is 0.2. So let's plot all of these points, and I'll start by drawing the asymptotes. So there is a horizontal asymptote at y equals 0, and a vertical asymptote at x equals a half. Notice the vertical asymptote goes right through the x-intercept of the function that was in the denominator. And that's one of the main properties of reciprocal functions. Whenever the denominator is 0, we know there's a vertical asymptote there. Okay, and now let's plot our points. So this branch of the hyperbola is going to look like this. Make sure you never cross your horizontal or vertical asymptotes. And then the function exists in this quadrant as well. So the blue function is our reciprocal function, the 1 over 2x minus 1. And we got all of its y values just by doing the reciprocals of all the y values of 2x minus 1. So notice when the linear function was 0, the reciprocal is undefined. And when the linear function was 1 or -1, the reciprocal function was in the same spot. And that's because the reciprocal of 1 or -1 is itself. A couple other properties I want you to notice. When the linear function has negative y values, so does the reciprocal function. And when the linear function has positive y values, so does the reciprocal function. The reciprocal of something just means 1 over it, so it doesn't change its sign. And notice the linear function is increasing over its entire domain, and the reciprocal function is decreasing over its entire domain. Alright, so that's it for reciprocal linear functions. Just know you're going to get these two branches that form what's called a hyperbola. So there's going to be a horizontal asymptote at y equals 0, and a vertical asymptote at x equals whatever makes the denominator 0. Alright, let's move on to reciprocal quadratic functions, and I'm going to take you through 3 examples, b, c, and d. Specifically 3 examples because there are 3 options for what the reciprocal quadratic could look like, and that all depends on how many zeros the quadratic in the denominator has. So this quadratic, it may be helpful if I rewrite this in factored form for you. So in factored form, it would equal 1 over, and let me factor this by finding the numbers that have a product of -15 and a sum of -2. Those numbers are -5 and 3, so this factors to x minus 5 times x plus 3. Having it in factored form, we can tell that the function in the denominator has two zeros at 5 and negative 3. So let me divide my work into two parts again. One part for that function that's in the denominator, that x squared minus 2x minus 15 function, which we know factors to x minus 5 times x plus 3. And then also, we'll get some properties for the reciprocal function. So y equals 1 over that quadratic. Okay, so some key properties of a quadratic are going to be its x-intercepts and its vertex. We're going to need all of that information. So let's start with x-intercepts. That's probably easier since it's already in factored form. So x-intercepts are the x values that make y be 0. So how can that product be 0? If x is either equal to 5 or negative 3. So we have two x-intercepts, negative 3 and 5. The vertex, I actually really only care about the x-coordinate of the vertex right now. We'll get the y-coordinate when we do our table. To find the x-coordinate of the vertex, there's lots of different ways. Way number one, well, if you have two x-intercepts, we know parabolas are symmetrical, so we could just add them, divide by 2, and that would tell us the x value of the vertex. But I'm actually going to use a different shortcut. I'm going to use the negative b over 2a shortcut, and that'll tell me the x-coordinate of the vertex. So if the function is in standard form, the coefficient of the x squared is a, the coefficient of the x is b, and the constant is c. So in this equation, we only need b and a. So negative b, so negative 2, well that's just 2, over 2 times the a value is just 1, 2 over 2, 1. So the x-coordinate of the vertex is 1. So when I get a table of values for this quadratic function, I need to make sure that in this table of values, the vertex is in the very middle. So I need the x-coordinate of the vertex to be in the very middle. I also need to make sure that the x-intercepts are included in the table. And I need to make sure I pick points between the vertex and the x-intercepts. So let me just do 0 and 2. And then also on either side of the x-intercepts. So to the left of negative 3, I could choose negative 4. And to the right of 5, I could choose 6. So in this table, we have the x-coordinate of the vertex in the very middle. We have an x-intercept here and an x-intercept here. And then it's really important that we choose points within each of these intervals to make sure when we graph the reciprocal, we get every piece of the graph. Okay, now let's calculate the y values that go with each of those x values. And remember, this is just the table for the function that's in the denominator. It's just the table for this quadratic. So let me plug each of the x values into this function right here and get its y values. Okay, those are all the y values that go with each of those x values. So let me plot each pair of points, and we'll see what the quadratic looks like. Alright, there's a rough sketch of the quadratic. Now we'll use its properties to come up with the graph of its reciprocal. So for the reciprocal, let's start by writing its asymptotes. It's going to have a horizontal asymptote and actually two vertical asymptotes. The horizontal asymptote, since the function in the denominator is degree 2 and the function in the numerator is degree 0, whenever the denominator function is a higher degree than the numerator, it has a horizontal asymptote at y equals 0. Vertical asymptotes will occur at any x values that make the denominator be 0. And the function in the denominator, this x squared minus 2x minus 15 function, is 0 at those two x values, negative 3 and 5. So we'll find two vertical asymptotes, one at negative 3 and another at x equals 5. So when we make our table of values for this function, we're going to use the exact same x values as we used for that quadratic function. Notice that in this table, we have a vertical asymptote there, and we have our vertical asymptote here. It's important those are both in the table. And the x-coordinate of the vertex, where the vertex was for the quadratic, that's where there's going to be a local max or min for the reciprocal function. In this case, it's going to be a local max, but you'll see why once I show you the graph. Alright, let's get all the y values that go with each of these x values by just doing the reciprocal of all of these y values. Because I got all of those y values by plugging the x's into the quadratic, and that's the function that is in the denominator here. So I just have to do the reciprocal of all of them, and then I get the y values that go with the reciprocal function. So when I do 1 over 9, I get about 0.11. 1 over 0 is undefined, that's why there's a vertical asymptote there. 1 over negative 15 is about negative 0.07. 1 over negative 16 is about negative 0.06. and then 1 over negative 15 again, 1 over 0 again, and 1 over 9 again. So there are the points that will give me a good shape of the reciprocal quadratic function. So let's start by graphing its asymptotes, the horizontal at y equals 0 and the two vertical asymptotes. And notice those vertical asymptotes occur at the exact places where the quadratic function was equal to 0, because we're graphing its reciprocal. So it would make it 1 over 0, which is undefined. And this function is going to appear in three sections. It's going to appear here, here, and here. Let's look. Our first point is negative 4, 0.11. So it's right about here. And then we also had a point at 6, 0.11 over here. And now let me get the points that were in between here. It was at 1, negative 0.06. Now I'm going to exaggerate how low that point is just for effect, but it's around right here. And then at 0 and 2, the point was down slightly more to negative 0.07, so slightly lower. Okay, so I've plotted all the points I know, and now this red quadratic function, it's not perfect, so what I'm about to do next isn't going to be exactly accurate, but let's pretend that that red function, I drew it perfectly. I know that whenever the quadratic function is 1 or negative 1, the reciprocal is going to be the same. So I could put another point here, and another point here, and here. So that tells me that the function is going to look something like... Now that middle part was a little hard for me to do, but it should look kind of parabola shaped, but really flat at the top there. Let me just show you Desmos's version of this graph so you can see how we did. Okay, here's Desmos's version of that same function. It looks like we did pretty good. We've got the function in the correct three sections, we've got the correct asymptotes, and we have that flat-shaped parabola as well. So our graph is not bad at all. Once again, I want you to notice that whenever the quadratic function has positive y values, its reciprocal also has positive y values. And when the quadratic has negative y values in that same domain, the reciprocal function has negative y values. Also notice, whenever the quadratic function is decreasing, so over that domain right there, what's happening to the reciprocal function? It's increasing on both of those sections. And once the quadratic function switches to increasing, the reciprocal function does the opposite. It switches to decreasing. Alright, that's our first quadratic done. Let's try two more to get the other two options. So this one had two vertical asymptotes. Let's see what the other two reciprocal quadratics look like. Okay, we have another reciprocal quadratic. This time the reciprocal quadratic actually has no vertical asymptotes. Let's look at why. So let's start by dividing our work into two parts again. One part for that quadratic that is in the denominator, and one part for the actual reciprocal quadratic, the one we're actually interested in. In the last question, I told you the general properties we want of the quadratic are its x-intercepts and the x-coordinate of the vertex. So x-intercepts, we would try and figure out what values of x would make y equal to 0. And if we tried to do this, we would end up getting x equals plus or minus the square root of negative 4, which we know has no real solutions. Therefore, no x-intercepts. What does that tell me about the reciprocal? It tells me there's no way the denominator can be 0, which means there are going to be no vertical asymptotes. But I'll write that down in a second. Let's find the x-coordinate of the vertex. And I told you the formula we could use to find that is always negative b over 2a. This equation, maybe it's helpful for you if we think of it as x squared plus 0x plus 4. Just makes it obvious to you that the b value is 0. Our a value is 1, c is 4. So when I use this formula, I do negative 0 over 2 times 1. That's just 0. The x-coordinate of the vertex is 0. So when I make my table, once again, I need to make sure that the x-coordinate of the vertex is centered. So I'll put 0 in the middle. Now I don't have any x-intercepts to include, so I just have to make sure I choose points on either side of that x-coordinate of the vertex. So I'll just choose negative 1, negative 2, negative 3, and on this side 1, 2, and 3. And then I'll plug each of those into my x squared plus 4 function, and I'll get the y values. So just square each of them and add 4. And now let's use those points to help us get a table of values for the reciprocal. So the reciprocal, let's write its asymptotes first. It still has a horizontal asymptote at y equals 0. Vertical asymptote, though, there's no way the denominator can be 0, so it has no vertical asymptotes. So when we do the table, we're going to keep the exact same x values, and we're going to get the y values by doing 1 over the y values. So same x values, they were -3 to 3, and in the middle, since there is an x vertex in the middle of that one, I know that it's going to create a local max or min here, and once again, I know this one's going to be a local max, and we'll see that when we do the graph. And then let's just calculate the y's by doing 1 over each of these y values. So 1 over 13 is about 0.08, 1 over 8 is 0.125, 1 over 5 is 0.2, 1 over 4 is 0.25, and then it's going to start going back down. 1 over 5 again, 0.2, 1 over 8 again, and then 1 over 13. Notice that 0.25 is that local max. It's the highest it's going to go. So now let's graph both of these functions. We'll graph the quadratic that's in the denominator and its reciprocal. Okay, so here is the quadratic y equals x squared plus 4. And now let's do its reciprocal. It had a horizontal asymptote at y equals 0. It had no vertical asymptotes, and I can see that because the quadratic has no x-intercepts, so there's no way the reciprocal could be undefined. So I'll just plot all of the points. And once again, these y values are very small, so I'm going to exaggerate them a bit. So that is our reciprocal function, our 1 over x squared plus 4 function. Let's check with Desmos to make sure ours looks good. There's the function there, the 1 over x squared plus 4 function. Perfect. Looks exactly like we wanted to. Notice some of these properties again. When this function is decreasing, the reciprocal function is increasing. And when the quadratic is increasing, its reciprocal is decreasing. Okay, part D, the last one. This one is going to be the third scenario for a reciprocal quadratic. So we did one that had 2 vertical asymptotes, one that had 0 vertical asymptotes. This one's going to have 1 vertical asymptote. And that's because there's going to be one way that the denominator could be 0. So let's look at this function. Oh, this is also the first time when I made the numerator something other than 1. It's still a constant, but it's 2. So what we're graphing is really 2 times the reciprocal quadratic function. So it's just going to be vertically stretched by a factor of 2. And I also factored the denominator for you. This quadratic, the numbers that multiply to 9 and add to -6 are -3 and -3, so it factors to x minus 3 times x minus 3, which is x minus 3 squared. So we're going to split our work into 2 sections again. One section for the quadratic function that's in the denominator, and one section for 2 times its reciprocal. So I'll actually write this version here. So keep in mind this one factors to x minus 3 squared. The key properties we want for a quadratic are its x-intercepts and its vertex. So x-intercepts, those are values of x that make y be 0. So when it's in factored form, it's easy to figure out what would make y be 0. If x minus 3 was 0, I'd have 0 squared, which is 0. So how can x minus 3 be 0 if x was 3? So there's one x-intercept, it's at an x value of 3. And if I want the x-coordinate of the vertex, now this is in vertex form, so I know it's at 3. But if we were to use that same negative b over 2a trick, a is 1, b is -6, I would get -6, so 6 over 2 times 1, that's 3. Notice the x-intercept and the vertex are the same, so its vertex actually lands on the x-intercept. That's why this quadratic only has one x-intercept. So when I make its table, make sure you put the x-intercept and the vertex right in the middle. So 3. And then I'll choose some points on either side. So how about 2, 1, 0, and 4, 5, 6. Plug each of those in to this equation, and we'll get the y values to go with each of them. Okay, so this is what the quadratic would look like. Let's graph that. So there's the quadratic. This is the x minus 3 squared function. Now let's use properties of that function to graph 2 times its reciprocal. So its reciprocal is going to have a horizontal asymptote at y equals 0. and a vertical asymptote at x equals whatever makes the denominator 0. And we figured out that 3 makes the denominator 0 because that's an x-intercept of the function in the denominator. So a vertical asymptote at x equals 3. And then when we make our table of values, we're going to keep all of the same x values, and then 2 times the reciprocal of the y values. We have to multiply it by 2 because the number in the numerator is a 2, not a 1. So we'll do the reciprocals and multiply them by 2. So I can just write 2 over y. So I'll rewrite all of the x values, and then I'll do 2 divided by each of the y values. So 2 over 9 is 0.22, 2 over 4 is a half, 2 over 1 is 2, 2 over 0 is undefined. And let's keep going. Let's do the reciprocals of these. 2 over 1 is 2, 2 over 4 is a half, and 2 over 9 is again 0.22. So I could plot all of these points and get a good shape for my reciprocal quadratic function. Alright, there we go. Notice once again, when the quadratic is decreasing, the reciprocal is increasing, and vice versa. When the quadratic is increasing, its reciprocal is decreasing. They don't intersect at y values of 1 anymore because this function's been multiplied by 2. When the original function is 1, the reciprocal is up here at 2. It's 2 over the 1 value. Also notice, when the quadratic has positive y values, so does its reciprocal. So in both of those sections, positive y values, because the quadratic that was in the denominator had positive y values as well. Okay, so notice the 3 shapes it could take when we have a reciprocal quadratic. It could look like this if there is one vertical asymptote. It could look like this if there is no vertical asymptotes. And it could look like this if there are 2 vertical asymptotes. Alright, so that's it for this lesson. Hopefully you now know how to graph reciprocal, linear, and quadratic functions.